So we want to thank you for joining us for the second session with Don Boomer. We will answer all of your questions live on the air.
Some of them.
Some of them. Well, we thank you for filling out the form, and you've given us a lot of good questions, and Don will address them. But first, he's going to do a brief presentation on troubleshooting. So without further ado, Don Boomer, take it away.
Yay. So kind of what I've done here, I've sort of combined a lot of questions. A lot of the questions really are the same thing. Every situation is different, but the most common problem that I get asked about is a gain structure issue. Gain structure is different than just level. Level's just plain voltage, but gain structure has to do with dynamic range. And that's really the most important thing with wireless. So I get a lot of people, they'll put in an antenna in a distro system, and then they'll say, well, I'm getting all this noise in my receivers. And what you're getting is, again, is a gain structure issue. Your receivers, when you buy new wireless mics, they're calibrated that considering that you're going to use the little whip antennas, which don't have much gain. So all of a sudden, when you have a good antenna and a distro, you have some gain in the system. You have 6 dB, you have 4 times the signal going into your receiver that then the receiver expects. That's not a problem, it's a good thing, but you have to adjust for it. In particular, well, all wireless mics should be adjusted for it, but in particular, Sennheiser, the older analog Sennheisers, not the new digital stuff, seem to be particularly touchy about this. You really have to set it right. And so if you have 6 dB of additional gain, and this changes, it could be more, it could be less, but let's just say you have 6 dB of gain. That means your squelch setting is 6 dB off, and you're getting 6 dB more input into that receiver, which could cause it to overload. So you can't have a receiver overload, right? If you do any audio work, if you do any recording with digital recorders, you know, once you go over, it gets really ugly really fast. And the squelch problem, again, is the squelch is basically a system. Let's see here, that when your signal drops below a certain point, it's essentially, we figure it's silence, but there's always a little bit of garbage. So the squelch setting actually mutes your output when the level falls below a certain level. On the audio side, it's a gate. But on the radio side, it kind of sets the distance that your antenna will go out searching for a signal. So the squelch system, most squelch systems have what's called a pilot tone. So while your microphone, you're talking into your mic and your speech is going through the air, you know, and it's being what you expect it to be, there's also an ultrasonic code that's built into that. And when the receiver sees the signal from you talking and that code, it opens up because it knows that's what you want to do. If you stop talking and you get to be near silence, the receiver won't see that anymore. It will lock down. So essentially, what that means is it's sort of it's setting a distance, kind of, right? So if you need to get your wireless microphone, let's just say 100 feet away from your antenna, and that's as far as you're ever going to be, then you need to take your microphone out 100 feet from your antenna, whatever your system is, and adjust the squelch so that it works at 100 feet, but at 110 feet, it stops working. In other words, you turn the squelch up, because if you don't, and you stop talking or you turn off your mic, once it loses that pilot tone, it's going to go out into the distance and try to find it again, but it's not there. So inevitably, it's just going to find noise, and you're going to hear a bunch of noise and hiss. It's going to get really loud, in your system, right? If your squelch isn't adjusted right, and somebody turns off the transmitter, when they turn off the transmitter, the pilot tone goes away. So it then goes, oh, I better go look for another transmitter, and it'll start searching really far. So and it'll find noise, right? Because there's noise everywhere. It doesn't have to be a particularly dedicated noise source. I mean, there's just noise in the air from everything. So we want to set that squelch setting. Really, you should do this. You should set your system when you get an antenna and a distro. You need to reset the squelch because it's going to be off by probably 6 dB. Now, one way to do that is to pad the antenna. So I think most people are kind of under the mistaken impression that their antenna doesn't go far enough. Your antenna goes forever, right? It literally goes tens of thousands of miles finding signal. It is finding signal all the way from the other side of the planet. But that signal is so weak that it's buried down in the noise and you can't pull it out by itself. But the antenna is picking it up. So it's not that your antenna is not strong enough. You have to kind of think about it a different way. What it is that the noise floor is too high. That's really the issue. It's not that the antenna isn't picking up the signal. It's just that the noise floor is to a point where you don't have, 20 dB of headroom, carrier to noise ratio, right? So if we look at this, if we were looking on a scanner and we see our mic signal, you see it's coming in at like -62 or something. And our noise floor that we measure, of course, it wouldn't be a perfect straight line like this, but our noise floor is -92. That gives us a dynamic range of 30 dB. That's very good. That'll probably be rock solid. You won't have any problems at all. Okay, so why would we want to change this? Well, if we put a 6 dB pad in the antenna, in other words, we're going to, on purpose, weaken the signal coming from the antenna and going into the distro and into the receivers. I know that sounds backwards, but if you do that, you still have that same 30 dB of carrier to noise ratio, but now we've reduced the noise floor from -92 to -98, right? And so what that means is that your receiver sensitivity is based on the noise floor, right? So because I have 30 dB of dynamic range, I can waste that 6 dB. I don't need it. I still have my 30. I have plenty of signal. But when I drop the noise floor 6 dB, it improves the receiver's sensitivity by 6 dB, right? If you go over and read one of our guys, Ike Zimble in Canada, wrote an article in ProSound Web, and he's saying even with 200-foot cable runs, he's putting 6 dB pads in his antenna. Now, most people would go, 200-foot cable run, I've got to put a line amp in. No, we don't want you to put that line amp in. As long as you've got the carrier to noise ratio, you're in great shape. The signal could drop 10 or 15 dB more, and I'd probably still be good all day. So this actually improves your radio's ability, its sensitivity. This makes your radio better. Radios, given the choice of working at high level or low level, would prefer to work at their lowest level, right? That works. Now there's, you can exceed this, you can go beyond what works. But by putting that pad in there, you improve the sensitivity of your radio, and you haven't changed your dynamic range. So what does that mean? So there's these little BNC to BNC attenuators. This is a clip from Amazon. You can find these things anywhere. Actually, I think I found some $12 ones. It's literally two resistors inside that mechanical package. So just about anything works. There may be mechanical considerations. So you probably can work with cheap ones all day long on an installed system. If this is a portable system, you're tearing it down every day, then you might want to buy a little more expensive ones. But anyway, they're just BNC to BNC. So you just put that in line with your antenna coming in, and that's going to take the level of your system back down to what your radio expected out of the box. It's going to get rid of that noise, and it's going to make your radios better. So if you're hearing noise with your transmitters turned off, which like almost always happens with like Sennheiser G3s and G4s, because I don't know the circuit, but it seems to me they sort of work from the bottom up instead of the top down, the way other manufacturers do, which there's nothing wrong with at all. It's just a system, and so we need to do things that support their system, and so this is how you do it. Okay, so thank you. I got a bunch of questions that were submitted, I guess, when people signed up to watch this. I picked out the ones that I think are most common. I would suggest, though, I have to tell you, some of the questions are so truncated, they're so short, I'm not exactly sure what you're looking for. So if you send in questions again, then please do. If they're 2 or 3 sentences long, it works a whole lot better than if they're just 5 words, because sometimes I don't exactly know where you're going. But this is one I get from time to time. How do you rule out the difference between equipment problems and environmental issues? And of course, if you have a bench and you have all the instruments to test stuff, well, that's how you do it. But if you're out in the field and you don't have a bunch of stuff, it's hard to know. Are my electronics causing a problem, making this noise? Or is it something in the air? Is it RF floating in the air? And people call me, my antenna's not working. One of the things you can try. So if you have a system, you have a distro, or you have a combiner. If you're talking about inner monitors, or you're talking about transmitters. So let's say you've got a system. You're using a distro 4, you've got an antenna plugged into it, you're running to 4 receivers, and 3 of them are terribly noisy, but 1 of them is okay. 1 of them is fine, and the other 3 have some problems or a lot of problems. So how do you know? So you could have 3 bad channels in your distro. That's possible. It's not really likely. Mostly the distros fail, they just shut off. But it's possible that you've got bad amps. So how are you going to know? Well, what I would have you do is, so if channels 1, 2, and 3 are bad, and channel 4 is good, let's just say, take the receiver from channel 4 and plug it in place of channel 1 that was bad, and change the channel of what was channel 4 to what the channel of channel 1 was, okay? Then put channel 1 into channel 4 and swap the frequencies again. So you're doing substitutions. Really, that's really all you can do without test equipment. So if channel 4 now in channel 1 and set to the frequency of channel 1 still has a problem, then it would point towards something in the equipment, right? It would point towards the distro or something in front of it not working properly. But if all of a sudden it works, then that's going to tell me, and far more common, 99 to 1, the problem is that you have channel interference. Your channel selection is a problem. Now, you may have done it with Wireless Workbench or some other frequency coordination program, and you still have a problem. Well, that's because you're in an environment that's causing a problem at those frequencies. So Wireless Workbench does make some assumptions, and you might have something inside your building it just can't figure out. So you might get a different answer, but it's probably your channel count. I mean, the other thing you could do, if it's possible, take all this stuff home, plug it in your garage, and see if it works in your garage. That's going to tell you that you have a local problem, right? So if unbeknownst to you, there's an X-ray machine in the closet in the back of the room, that's not going to happen in your garage. Your channel assignment still may be a problem, but basically the best thing to do is substitute, because if one channel is working, right, if one channel is clean and clear and everything it's supposed to be, that's telling me that your antenna is working, your coax cables are working, and the distro is probably working. It's still a possibility that you have 3 bad channels and 1 good channel, but I don't win the lotto that often. It's a really big chance. So it's possible, but it's not very likely. It's much more likely that you have frequency coordination issues. And if you're using the built-in auto find me a channel, that it just doesn't work very well in a lot of situations anymore. Okay, so antenna proximity. When you have both a receiving antenna and you have an IEM transmitting antenna, you don't want the transmitter to get into the receiving antennas as much as you can avoid it. Now, it's going to happen. No matter what you do, it's going to bounce off the back wall and it's going to come and hit your receiving antennas. You're never going to make it 0 unless you're in separate facilities. Okay, so the idea is we're trying to get as much as possible. A lot of these things, a lot of problems that happen are the answer is not black and white. I talk about, the straw breaking the camel's back. And most of the time these problems, okay, it's a straw in the camel's back, but how big is the straw? So we'd like to eliminate the straw, but if we can't eliminate it, we'd like to make the straw smaller, right? Okay, so let's think about antennas. So if the red one at the top there were a CP beam, a helical antenna that you use for your in-ear monitors, and the blue was a diversity fin or something like that you use for your wireless mics. Okay, if you mount them both on the same wall at some distance apart, doesn't matter what it is, at some point those two things are going to cross, right? Because it's real. I drew it. Actually, I should turn the arrow around going into the blue one. It's going in. One's going out, one's going in. But there's a place at where they cross. And once you get farther than that, you're getting more direct signal into it. So this is, if you think about this the same way you would think about a microphone and a speaker, right? At 2 feet, I can't point my microphone into my speaker. At 100 feet, I can, because I've got so much attenuation with distance, right? So as you can see, we've got a point where it crosses over, and beyond that, it's starting to interfere with each other. However, as you continue to go to the right, you're losing signal strength on the transmitter because you're farther away from it. You're gaining strength on the other, but that's not going to matter. So you're kind of it's kind of self-healing as it goes farther away, but up close it's a problem. So if we split these apart some distance, and the answer is 100 feet's the best, but who's going to do that? I mean, that would cause other problems. The farther you can get them apart, the less interference you're going to have. But as we split these apart, you see we move that distance farther out. So in practice, you'd really like to get these at least 6 feet apart, 10 or 12. Much beyond that, it's really not going to make any difference, because now you're going to get so many reflections off everything else that, I mean, we're only dealing with the straight primary signal. You're going to have thousands of reflections. So you can't escape this. But by spreading them farther apart, you're moving that intersection a little farther out. if possible. So in a portable situation, if you've got your antennas up on mic stands, for example, you might also be able to move your receiving antenna a little closer to your transmitters. And that, in addition to lateral distance, that gives you some additional distance before you get to that intersection. So if you move, so if you got a D-fin and a CP beam and they're on mic stands, and if you can move your D-fin 2 feet closer to your transmitter, it's going to make a little bit of difference. In other words, we're never going to get rid of this straw, but we're going to make it smaller and smaller. So we'd like to make it as small as we can get away with, and go from there. So most of the time, you're up against physical limitations. You can only go so far. You can't tear down a wall and move it 20 feet out. Not going to happen, right? So you can't fix everything. You try to minimize as many things as you can. We'll take as many straws off or minimize as many straws as we can. And that's what you've got to work with, So you're not going to make this perfect. There's just too much interaction all the time. I get questions about antenna placement, and the answer is always the same. Point the antenna at the transmitter, maintain line of sight, and try not to point the antenna any place where your transmitters won't be, because inevitably they're going to pick up interference. Excuse me a second. Okay, so if we're talking about a football field, and we want to mount the antenna on the press box, which is up at 12 o'clock, he asked about an omni and a directional antenna. So an omni is most likely a poor choice because it's going to pick up in all directions, right? Where a directional antenna, like a D-fin, is only going to pick up the field. Now, I should tell you, the pickup doesn't stop where these circles are. That yellow circle keeps getting bigger and bigger and bigger and bigger and bigger for thousands of miles, okay? It gets weaker and weaker as it does, but it's going to cover the whole field. If you have sufficient dynamic range, it's not a problem. If your dynamic range is a little more limited, then the directional antenna is going to give you a better dynamic range, because the omnidirectional antenna is also picking up the parking lot on the other side of the field there and everything else. So it's picking up all these other areas that nobody's ever going to talk in, assuming nobody's ever going to talk there. Now, that's a different story if you've got to pick up the parking lot as well. But assuming that you're only going to pick up wireless mics on the sideline or on the field, you're picking up all that extra junk, and that's increasing your noise floor. Now, that doesn't mean it won't work, but it is making it worse, right? So we're limiting our dynamic range. If you've got 40 dB of dynamic range, you can get away with it. But it's you don't have enough straws on the camel's back, but using an omni in this case is making that straw bigger and heavier. So you want to use a directional antenna if possible for what I consider normal. I should share with you because honestly, I didn't expect it to happen. I had a customer call me last week that's actually using one of our D-architectural antennas down on the field. So he's the band director and they're picking up the band. And so he's using a D-architectural that he put on a mic stand. You'd have to put a clip on it. And actually putting it on the track, so it would be down on the brick reddish part. But he said from the 50-yard line, it covers the whole football field. I didn't expect it to have that much distance, and it may be that he has an extremely low noise floor, right? So if we were trying to do this at the high school next to Times Square, we're probably not going to have that happen. But for most places out of a big metropolitan area. I thought that was kind of interesting. because I didn't expect it to have that much range. But again, antennas go forever. It's just the dynamic range that makes it work or not. Okay, so if you've got an L-shaped room, you have to point the antenna at the transmitters. Now, in his question, he said, I can't put it in the corners. And I don't know whether he meant the inside corner or the outside corner or both corners. It can't go there in this case. Well, that's a shame, because you could put a D-fin or a D-architectural. If you were to put it in the upper right-hand corner, it would cover that entire L shape, right? Because you've got a 90-degree angle. Just consider that to be a square or a rectangular building. It would cover the whole rectangular building. The fact that you've chopped part of it out doesn't really matter in this case. But he can't do that for whatever reason. He can't do that. So so you have some choices. It's always about trade-offs. If you were to move that antenna over to where I show it here, you're going to cover one side of that L really well, and you're going to cover the other side partially and partially not. So, you know, you can kind of, if you could spin that antenna a little bit, you can play with where this triangle is going to go, and you could get better coverage down in that room. But when you do that, you're going to be giving up, you give up the coverage in the upper right-hand corner. However, I should say, antennas kind of don't have any pattern when you're close to them. So like a microphone, cardioid microphone is supposed to be dead on the backside. Well, I guarantee you, if I'm 2 inches away from the backside and I scream into it, it's going to pick it up, right? It's not dead. If you get out 20 feet or something, it's pretty much dead, but it's always picking up a little bit. So that upper corner that we're missing, because we're so close to the antenna, is going to have some reasonable amount of coverage. So you could play with it this way. This would be a compromise. The way to do it and not have a problem is to put antennas on the two long sides and shoot into the room. Now everything is covered, and you haven't used that corner. T-architecturals, D-fins. I don't know how big a room. See, that's the other thing. He didn't tell me how big the room is. So if we go back, we go back to this, you know, well, this one's going to work okay. But this one, if those rooms are 300 feet long, this is not going to work quite like if they're 60 or 80 feet long, right? So we have to, I mean, just expand the geometry out, you see you're going to miss a lot more. So the size is going to make a difference. In this case, if each one of those rooms was 300 feet long, this would cover it. You could use 2 D-fins or probably 2 architectural, diversity architecturals, depending, but that would cover it. So that's, I mean, you have to cover your areas. Well, I should mention, so one mistake, or not a mistake, but it's definitely not a best practice. People think they can take, if they're using 2 paddles or 2 whips, they think, well, I could put one whip in one corner of the room, or, you know, one side of the L, and I could put the other whip in the other side of the L, and I'd be covered. And the answer is, yeah, you would, but you give up diversity when you do that, or you give up most of your diversity when you do that. So there are spots that even when your antenna is polarized, there are spots that are going to go dead. They're mathematically predictable. They're very small, but if you stand in a certain bunch of 2-inch squares inside that room, there are spots, you know, high, low, middle, they're there, where you'll be dead just because of the physics of the waveforms, that it would switch over to your other antenna. But if your other antenna is not there, you have nothing to switch to. So that kind of a system, again, it's going to depend on size. It's going to depend where you are, because obviously if you're way out in the country, I shouldn't say way out in the country, that doesn't mean anything anymore. If you're in a very low interference area, you can you can get away with things that you can't if you're in a high interference area. So that's kind of the way we solve that one. Is using high power versus standard, or I guess even low, acceptable if one frequency is giving you trouble? And the answer is, yeah. I mean, you do what you got to do to make it work. You just have to understand that. So if I have 8 microphones and I have 7 of them turned on low power and I have 1 of them turned on high power, what does that mean? Well, the one that's on high power is creating more intermod than the ones that are on low power. Is that a problem? Don't know. It's not a good thing. We definitely don't want that to happen, but is it poison? And the answer is it just depends on your situation. So, you know, if you've got 30 dB or 40 dB of headroom, it's probably not a problem. If you're down to 25, then it may become a problem. But, you know, kind of the answer is if it works, do it. I mean, so I don't have a particular problem with doing this. I don't want to do it, but if I have to do it, that's what we do. We do what we have to make it go. This could be a perfectly good answer. Again, everything that we do depends on what our local interference level is. And that's always, you know, pretty much the unknown unless you measure it. Which is why I keep telling people, you got to measure. This stuff's invisible. We're guessing, you know. We used to get away with guesses a lot because we didn't have so much congestion. But now we don't have much frequency left. And so guessing is getting much, much harder to do. So measuring is definitely something you want to do if you can. And so, Adam, do we have any more questions that were sent in that I didn't cover?
So there were no other questions. I gave you everything I had, but we do have, looks like one question coming in now. Good opportunity.
Okay. Yeah, you guys, if you have questions, send them in on the chat line there.
Yep, you could just throw it in the Q&A or the chat, whatever's easiest. We've got about
either one. I'm sorry. Yeah, you got two.
Another 10 minutes. We can answer some questions for you. I've seen a few people try and use whip antennas not directly connected to the receiver, i.e. putting the antenna on a mic and running the cable to the receiver. Can you talk about why that's a poor choice?
If it's a half-wave antenna, it's not a poor choice. I mean, you know, it is what it is. It's a whip antenna. If it's a quarter-wave antenna, so a quarter-wave antenna is a piece of wire, and then it bends up, so it's an L shape, right? It's a piece of wire coming in. That's your BNC connector, and then there's a 90-degree bend, and it goes up. That's a quarter-wave antenna. If it's a half-wave antenna, there's 2 of those. There's one to the hot side of the BNC, and there's one to the ground side of the BNC, because your antenna has to be grounded. So what that means is you can put the quarter-wave antenna on the chassis of your receiver, because that chassis has some size, and that acts as what they call a ground plane, right? So you could take your quarter wave antenna and you could put a big piece of metal under it, you know, I don't know, bigger than a pizza pan, I guess. You could drill a hole in the middle and do that, and then that would work. But the quarter wave antennas are they're missing half, right? That's what a half wave antenna does. And so when you have a half wave antenna, the other half of the antenna itself is the ground plane. Sometimes those wires get twisted and curled, but there's just 2 wires, right? So it's just it's an L up and an L down. That's a half wave antenna, and the quarter wave only has one of those elements. So if you know what your antenna is, unfortunately, it's almost impossible to look at it and see. I never really thought about it. I suppose there's some way you could measure it, but that's probably ugly. So you have to know that you've got a half wave antenna. So typically, Unless it says otherwise in your owner's manual, I would assume every little whip you see it to be quarter wave because it's cheaper. It's cheaper for the manufacturer to include it. So, and it works fine on the chassis or on a big honking piece of metal. I guess you could, if you had a metal equipment rack, you could drill a hole and you could put it in that, and the rack itself would act as the other half. But yeah, that's kind of the deal there.
Great, Don. Yeah, that comes up a lot. Can you remote mount quarter wave antennas? So I think it's
yeah, quarters you can't.
Yeah, you've demystified it for us. So they're
well, I should say you shouldn't. They won't 100% fail, but they won't work very well. So
you can certainly go for the new RFNU 2-channel remote kit if you need something better.
Yeah, we've got a little kit now. A lot of people, you know, like in a classroom or something where they only need a couple of wireless mics. They don't need a distro and they don't need a big antennas because, you know, they're only working at 30 or 40 feet. But they've got quarter wave antennas and they put the receivers in the closet. And now you don't have line of sight. And when you drop your line of sight, you lose a ton of good signal quality. So now we've got a little kit to where you can mount the antennas outside and connect it back to two receivers without using the distro. It's a passive distro, which is fine on a couple like that.
I went ahead and shared that kit in the chat window so everybody could take a look. So it looks like no more questions are coming in. Can you believe it, Don? You answered everybody's questions and there's no more questions.
Everybody's questions. Wow. In record time too.
In record time. Oh, here we go. I knew there was going to be one more. Using a diversity fin D-fin, diversity fin. I'm reading too fast here. Can I loom the two cables together without concern for affecting performance? And what length should I limit to?
Okay, so you're still going to use two cables and you just want to know if you can like tie them together with tape or something like that. If you're using 100% shielded cable, yes, you can. So if you're using the cable that we sell, RG8X, that's double shielded, yes, you can do that. But if you're using older style RG58 cable, no, the cables have crosstalk. So one cable will transmit into the other cable. So that's probably not a killer, but it is creating garbage. So we're trying to eliminate garbage. So we want to eliminate that as much as possible. And then I missed, there was a kind of a second half to that. Oh, yeah, how long? How long?
Length,
so
right.
So how long always depends where you are. Again, how long on top of a mountain in Idaho is different than how long in Times Square. We have a performance calculator on our website. You just go to performance tools and click on that. It depends what mics you have. It depends how far away you're going to get from your antenna, right? So if your wireless microphone is going to be 300 feet away from your antenna, that cable is going to have to be a lot shorter. If you're going to be 20 feet away, it can be longer because we're looking at the total loss. The loss through the air and the loss through the cable is bringing down our level closer and closer to the noise floor. So as a real general rule, you probably can get away with RG8X up to about 100 feet. If you got to go farther than that, then I would switch to a cable. Belden makes one called 9913, and it has half as much loss, so it can go twice as far. So you could do 200 feet with that. It's much bigger, it's much more expensive, and it's much harder to work with. But that's what you got to do if you've got to go a couple 100 feet. And for most people, much beyond a couple 100 feet starts getting to be risky. You should consider RF over fiber, which you can use at like 5 kilometers or something crazy apart.
Yep. 5 kilometers.
You know, so right. if you're doing a, you know, we run into this with people that do zone systems. because the antenna's got to be 800 feet away because that's where they got to be. There's just no way to do that with coax wire. You have to do that with fiber.
Awesome. Looks like we got time for one more question here. This is a good one. This comes up a lot. What's the possibility of using a helical and another antenna with IEMs? I'd like to use a whip or something similar for the area off stage of the monitor console.
So we're using two antennas? We want to
Yes,
cover.
I believe that's to kind of, it sounds to me like they're trying to do multi-zone.
Yeah, so you can do that. So, right, if I have to cover a stage and then I got to cover that way as well, you can take the output of your combiner, run it into a splitter, and run it into each antenna. Now you're sending half the power to each antenna, so you're cutting the power in half of each antenna by itself, but that's probably fine. So the problem with using a whip or a paddle, it works. The problem is if your belt packs move. Right. So if we can keep the belt packs perfectly aligned, it works fine. The problem is you almost can never do that. People are going to move, twist, bend, and when they do that, they get off the antennas. I should do it this way. Let's see. So they need to be polarized, and as you start turning one compared to the other, the receiver loses its ability to pick up the signal. So by the time it's all the way horizontal, it's only picking up less than 1% of the signal that it was picking up this way. So a helical antenna is transmitting the pattern in a circle. It's spinning. So it doesn't matter how you turn, you're always lined up with it. That's the problem. So if your secondary location can handle more hits, then you're probably okay doing that. But a helical is a better way to go. It's just, if you want rock solid performance, you need to use a helical. If you can suffer some dropouts, most of these, even before they drop out, they get noisy. The frequency response goes bad. They get a little distorted. They get a little noisy, even before it drops out. But that's what's going to happen.
Great. Yeah, we have a few people using multiple 2 CP beams with Combine 4, for example, to get more coverage area where they roam around.
Yeah, if you need to cover this way and that way, that's what you do. You can do that. Yeah.
Well, great, Don. I think we've got to the point here where we're good. I don't see any more questions, but you guys can always send us an email, adam@rfnu.com or don@rfnu.com. Feel free to send us any questions you have. We weren't able to answer yours today, and definitely look out for this session next month where we do question answer number 3. So we're looking forward to your attendance on that, and I'll be sending out a feedback survey about how we did. So if you could fill that out for us, we'd be very grateful. We appreciate your time as always. Thanks again. And we hope you have a great rest of the day. Thanks, Dawn, as always. I learn something every time. So I appreciate all the tutelage.
You bet. You bet. Have a good one,
right,
guys. Thanks for joining us.
Take care.